Okay, so for this session, we are going to have Dr. Stan Markov, the data science from Meridian Innovation Limited, as our first guest speaker right here in our CARES Hong Kong office. And his topic is going to be reliability, intelligence, performance monitoring, and lifetime prediction of thermal imaging sensors. Over to you, Dr. Stan Markov, please.
Thank you. Hello, everyone who is in the audience. And I would like to start with expressing our thanks to CARES for giving us this opportunity to share our efforts in the direction of reliability of our thermal imaging sensors, and also to participate in this forum, which so far I find quite educative. Very deductive presentations. So in my talk, I would give a brief overview of our company and our product, which basically presents then unique concerns about reliability. And I'll briefly state what these are from our current understanding and how we are trying to address them. In the last few slides, I will throw out a concept that we are exploring together with CARES as a working idea where we are trying to predict performance and lifetime expectations in real time of sensor, thermal imaging sensor in this case. So to start with, I would like to state that Meridian Innovation as a company was started with the vision to catalyze an explosion in diversifying applications for thermal imaging. Similar to what happened with visual sensors once they became manufactured by CMOS technology. So some of you may remember that before CMOS visual sensors, there were charge-coupled devices which provided black and white picture, basically. But stepping on the scaling path of CMOS technology allowed proliferation of visual sensors until the point at which they became ubiquitous, both in communication, in entertainment and social media, and of course, safety and numerous industrial applications. We see some potential for this to happen in the area of thermal imaging space, specifically in the spectrum of long-wave infrared, which corresponds to temperature by means of the emitted radiation from all objects that surround us. So Meridian was started in 2016, incorporated both in Singapore and Hong Kong, and had very dynamic already for 5th year now, from the striking up the first partnership with a fab that can process our CMOS wafers, to demonstrating the first working pixel, scaling to an array of focal point array of 5,000 pixels, building the first module, including lens and proper assembly and connection to an electronic system, and our product launch in 2019. And despite COVID, we were very fortunate that we were able to enter mass production in 2020. So what is unique about our technology is it is essentially a hybrid between the two existing technologies for sensing thermal radiation. And these are polarly opposite in some sense. You have the thermal power technology, which results in big pixels, but is relatively easy to manufacture. The problem with this is it cannot be scaled to provide a focal point array of large number of pixels. So it has relatively limited application. On the other extreme, you have microbolometers. That is a technology that involves a lot of exotic materials like vanadium oxide, for example, and is not compatible with standard CMOS manufacturing techniques. So the resulting product, although has very good properties for sensing and miniaturization of the pixel itself, has numerous issues in terms of scaling the volume of production, have not been shown that it can scale down the cost, and carries other complications like the necessity of mechanical shutter due to the type of operation and physical phenomena from which signal is derived. So Meridian Innovations concept relies on creating a hybrid architecture for the pixel and realizing it with standard CMOS and MEMS processes, including proprietary vacuum level packaging, wafer-to-wafer bonding, and this results in a relatively small pixel. Our starting proposition is at 45 micrometer, and second generation will be at smaller 35. That should be compared to current state of the art is of the order of 12 micron for microbolometer and about 100 at best, or 90 maybe, in the thermopile area. So that allows us to both reduce cost and scale to very large volume manufacturing and possibly deploy en masse in infrastructure type of environment. That entails, of course, its own specific concerns about reliability that I'll address shortly. But whether there is a demand for this sensor, you may ask. This slide answers this very quickly. If you look what happened mostly as a result of the COVID situation emerging last year, the market for temperature sensing imagers is basically doubled over 1 year. And the core drivers for that are the thermography and surveillance. These are the biggest drivers that have almost tripled. So there are really a large number of applications. So far, limit to the applicability has been cost and availability of sensors, and Meridian is trying to overcome that. So in this slide, there are a few applications from visually presented here from standard thermal guns that you may have seen here and there, now very, very often used for temperature screening at entrance of buildings, to mobile phone attachments that transform your mobile phone into a thermal gun, through systems where you can use thermal imaging as complementary to strengthen the ID authentication process and make it more secure. Then you have a number of applications in the domain of IoT and appliances, for example, smart air conditioning that is not only concerned with the measuring the ambient temperature, not only counting the number of people and adjusting the flow rate, but also being able to measure the skin temperature and obtain a metric of the level of comfort that people are experiencing in the ambience that is being controlled. You have, of course, the natural people counting and heat flow maps for managing crowd management or just people flow control. You have connected applications for these and the standard surveillance and monitoring at night or conditions where optical camera would underperform significantly. I already mentioned the development related to COVID requires screening for fever from a distance and various modes of realizing that, from thermal guns to personal mobile phones, through systems that are commonly deployed at airports, were commonly deployed at airports, but nowadays you start to see them more broadly available. So what is Meridian offering is a thermal sensor that is very small, of about 5,000 pixels of image. Each pixel has temperature readout, and it is not only the sensor but also development system that we are offering, and reference designs that our customers can deploy immediately or with minimal effort, since we also supply software development kits for that. So a typical system would connect to our sensor through our thermal imaging processor, which will basically do all the complicated stuff related to interfacing the sensor and transforming whatever signal each pixel outputs into temperature that can be handled easily with our software development kits for different languages. And here is a prototype of host system which we distribute as a development kit. But if we focus on reliability, our major concerns are here at the level of the thermal camera module. And people may understand different things when I say thermal camera module, maybe a bigger camera assembly, but in the context of my presentation, it will be this little guy that I'll be addressing. So I mentioned already that we provide reference design for various platforms here for appliances, but these different platforms involve different challenges. For example, cooktop monitor, microwave oven that integrates the sensor, air conditioning. These are challenging environments where the camera module will have to withstand temperature in the range of 85 degrees as demanded by our customers, and high humidity. So this raises a number of concerns. If you look at the consumer grade, then it is not so much about the elevated temperature, but if people want to use an attachment, as we discussed here, it must perform with certain accuracy tolerances. So maintaining this over given lifetime settings, for example, 1 or 2 years, is very important, because this has the meaning of thermal measuring instrument, temperature measuring instrument. And then we go to an extreme case where we have developed some library that helps our customers quickly realize a fever screening system. It's crucially important that the parameters do not change, because if it is, over time, if the sensor goes out of its spec, then the system can miss basically true positive cases with fever. So the whole system becomes less reliable, not reliable, not even to spec. So what are the concerns in terms of reliability? The camera module actually has several key components. The sensor chip is this little black square that is depicted here in the schematic. And this chip contains the focal point array. There are 5,000 pixels, each of which is vulnerable in some sense. But then this chip is attached to the PCBA in a way that must ensure efficient thermal conduction to the case, to the lens case, which is of aluminum and disperses heat. Then you have a lens which is not an ordinary glass, but it is germanium material which is transmissive to infrared radiation, and otherwise it's opaque to visual light. Glass, for example, or typical optical lenses for visual light are not suitable. So the transmissivity, however, is depending on the so-called anti-reflective coating, which improves the transmissivity by a factor of about 40%. And it is quite sensitive to high temperature. And finally, the chip and lens holder are bonded to the PCBA by epoxy, which has its own challenges and degradation over time that could lead either to failure or just degraded thermal conduction path. But by far, I would say the major concern is at chip level, where you have various modes of failures and deterioration. So the complication there arises from the way that the MEMS system operates. A lot of sensors nowadays involve creation of a vacuum cavity in which a sensing element is exposed. Thermal imaging sensors operate in the same concept. Basically, there is some sensitive element that is realized in our case in one wafer together with the readout circuit, and then there is a so-called cup wafer, or here it is called window wafer as well, that is put on top, and the two wafers are bonded together. And so the strength of that bond is in some sense point of great concern. It is every manufacturer has their own proprietary process and procedures to establish the strength of the bond. But if that bond deteriorates, you get sudden loss of vacuum, and the performance of the sensor goes out the door immediately. Basically, you cannot sense heat anymore. So another issue is that no matter the conditions of bonding, even the bond is strong enough, there are trapped gas molecules inside the CMOS wafer, which will gradually be released during operation. So typically sensors of that sort have deposited a getter material inside the vacuum cavity that is able to absorb these gas molecules. Now, the properties of this assembly and the performance of the getter over time are also point of concern, as I will show you. And of course, over time, the sensitive membrane in a way that realizes the pixel, the sensing element to heat, can also deteriorate, particularly if exposed to temperature scenes which involve very high temperature. And so these are things that we are trying to understand and predict how long operational lifetime is and how performance potentially degrades over time. So here I show from literature a typical wafer map of thermal imaging sensor. In this case, this is a microbolometer, which has been subjected to thermal shock type of stress, where wafer is inserted after bonding. The wafer is subjected to very low temperature, -45 for some 30 minutes, and then suddenly moved to a very high temperature of +85 within 5-minute transition. My understanding is that this happens with dual chamber machines that can support 2 different temperatures and have an automated way of changing the devices under test from one chamber to another. And in this case, it is seen that after the thermal shock, at least in one one of these dyes completely lost any sensitivity to heat, no response to heat basically. So that typically happens when the bond between the two dyes is ruptured, or if there was a microcavity that was completely expanded during the thermal shock. Another major concern is, as I said, the interaction with the getter and the overall change in the sensitivity or response function over time. Again, an example of microbolometer here shows degradation over an aging period of 1,000 hours. Approximately 20% of the sensitivity is lost. What that means is if you today calibrate your sensor and you're able to accurately detect the ambient temperature and probably person's skin temperature, then in about a few months or a year, you will be underestimating both these temperatures. That's clearly not acceptable. So we're looking for ways to assess the amount of loss that we see in our process, and also how to counter that. Is it possible to accelerate this type of aging effect, let's call it, so that as we ship the product, it's already at a stable sensitivity and we don't see accuracy degradation over time. And here on the left, it's just showing the different gas molecules and their concentration, how it changes as a result of 2,000 hour stress at 150 degrees. Note that these two problems, the bond strength and the sensitivity degradation, are tested in a different way. For the bond strength, it was the sudden change in temperature that may trigger bond rupture by means of some kind of delamination, because you typically have different layers of materials that may have different thermal expansion coefficients. So this is the physical mechanism that you're driving, that you're accelerating and trying to stress. Whereas in the case of sensitivity, you're simply trying to accelerate the release of these gas molecules that I mentioned here that are trapped. You're trying to accelerate their release so that happens ideally before you ship the product out. So what we try to see is we acquired some equipment to be able to do wafer level testing ourselves and kind of try both issues to address both issues at the same time. Here what you see is a wafer that has been already bonded and diced along the streets, and these wafers are put in a chamber. We would typically have a control wafer that sits outside, doesn't undergo temperature stress or cycling, and other wafers of similar wafer maps and similar sensitivities and process for producing that undergo temperature cycling. In this case, it's different temperature extremes, but 10 cycles at the same temperature ramp, around 3 degrees per minute, which is the range that we can afford with our equipment. So what we see here, I report just normalized values, but basically you have the control wafer, which is in blue, and the wafer that underwent temperature cycling. And so here at that point, 2 wafers are tested, and then 1 wafer undergoes cycling at 10 to 70 and is tested, then undergoes 0 to 85 and is tested, and then the extreme range of minus 40 to plus 125, and we measure again. So what we see in this case is that we were unable to break any bond at all. and that overall the sensitivity followed a trend that doesn't seem to be dramatically altered by the means of temperature cycling. So this tells us that, okay, for the intended operational range, which is actually 0 to 85 in this specific case, the bond strength would appear good enough, but we cannot derive from this test, we cannot derive any predictability about how long that will be the case. So lifetime estimation is not possible from this test. As far as sensitivity is concerned, we see that difference from one wafer to another is more significant than what we incur in terms of variation of sensitivity as a result of the temperature cycling. On the right, I show merely that the distribution of the statistics of the amongst the different dyes that have been stressed remains roughly the same. Only outliers that have low sensitivity would be affected somewhat, but not to a great degree. So it is interesting to consider in real-time operation, how would any of these potential degradation and failure mechanisms would be manifested. And so here I compared two images in which one shows much sharper delineation of the subject, sharper contrast, and temperatures which are quite accurate for the setting, and considering the extreme of the scene and the segmented image. And in the other case is an image which was taken with a sensor that has degraded both in terms of lens and sensitivity. So you can see the transition between the hotter object, which is the person in this case, and the ambient background is a lot broader. So you lose both resolution in a way, focus, and the temperatures are appreciably lower as well as a result. So the question is that we are discussing with CARES and trying to come up with a concept of not only gathering information from real-time imaging and basically assessing, quantifying the amount of change that is undergoing in the sensor, but trying to estimate corrective settings in terms of calibration data, which can be altered in order to compensate for the errors induced by the degradation. So there is a large variation in how this could be implemented, but basically what we see as a working concept is continuous acquisition of thermal images from a number of sensors at different conditions, and training a deep learning model from which we can start to distinguish different types of errors, how they manifested, and how they correspond to a particular physical mechanism. And then finding a way to deploy that model in real time. It doesn't need to be applied to every single frame that is acquired during normal operation, but it is possible to sort of run the model once every so often and obtain information about any anomaly if present, and assess the remaining lifetime, or is the module close to failure. And some of the performance factors are available within a single image. If we look at the histogram, we can quickly establish a reference temperature for the background and subject's temperature, in this case, human. These can be related to ambient sensors that are alternative deployed within the final product. And there are various ways to assess contrast and chip temperature and so on. So with this, I would like to close and thank you for your attention and welcome your questions.
Thank you. Okay, thank you, Dr. Stan Markov, for sharing the experience of meridians in the thermal sensors, as well as the prediction of the remaining useful life of the sensors. Now, let us invite our next speaker, Mr. Peter Ng, Vice President Enabling Technology Group of ASM Pacific Technology Limited. And his topic would be enabling high reliability power modules. And over to you, Mr. Peter Ng, please.
Hi, good morning. Maybe now it should be good afternoon to everyone. So this is my honor to be here to together with the three speakers to talk about how to enable the power module or power system reliability. I think previous speaker they talk about basically down to individual component reliability, how to assess the reliability and lifetime prediction, and also they also introduce a number of ways to carry out the test to predict the life of the component. But I think this is something may not be applicable to everyone because most of us is using the power electronic to our application, our design. I think power electronics is not just confined as what Dr. Das mentioned is for wind turbine or even high-speed train or maybe an aircraft application. But in fact, I think you can see power electronics is widely using for every electronic system, from very high power like powertrain, wind turbine, EV, and solar panels, or maybe high-speed train. But in fact, they are also widely using for robotic, motor drive, or even home appliance. Even your PC and even the data center will use a lot of this kind of power device. So what's matter to most of us is how to utilize the power device and reliably. I think this is the major focus in my coming talk. Okay, ASM is a supplier to the equipment supplier for semiconductor and also electronic assembly. We're also working with the power electronic. We provide the equipment for wire bonding. We provide equipment for die attach, and we have the particular assembly line focused on the power electronic assembly. And even though we have also the assembly line solution for the image sensing. So this is also a lot of things related to the reliability. I think most of the speakers also mentioned the packaging is also one of the issues contributing to the reliability factor of the device. But I think in this talk, I'm not focused on this part, but I'm more focused on the application. How we do as a design. Why matter to us? We are not making a device, but we are using a lot of this power converter. Because when we're using design as equipment, I think you can see here, I can show to you. This is the machine we have designed, die attach, wire bonding, or even some advanced packaging equipment, some for light LED, laser diode, assembly equipment. But inside the machine, they will involve a lot electronic design will relate to the power electronic. Like power driver, motor driver. Our motor driver can range from just a few watts to 15 kilowatt. And we also had a high temperature control system, can be ranged from normally RMS power can be up to 300 watt to 1,000 watt. But the peak power can be up to 10 kilowatt. So we can see this is something challenging design for power electronic. So from this curve, you can see how the reliability impact to the cost. I think on one hand, if we want to design something reliable with a long, reliable lifetime, definitely you can see the cost will jet up, the design cost. But at the same time, if we consider if we can the cost of the product, include in case they fail during the warranty, you have to pay for the warranty, and also you will also the cost of the failure, and also the brand name of the company. So this is another cost curve. So in between, you can see that they will have some so-called optimum point. So if we can really design certain reliable enough, such that we can meet the customer expectation or even beyond expectation. At the same time, we can optimize the cost both between the design cost and also the cost of the failure. So in order to do this one, we start from not just from the testing, but we start from the understand how the design will affecting the file reliability. So the approach we adapt is basically we understand what's the critical component we use, particular power device, and secondly we take the approach we design for reliability rather than wait until they fail. So we from design start from the very beginning. We design something we can fulfill the expectation of the customer requirement. And definitely test is also important because no matter how you do the design, we still need to carry out design verification, validation to ensure that the thing is designed according to what you design and we expect. So in terms of the challenge to the ASM, we are in different industry. We're not in the wind turbine, we're not in the EV, but our consideration may be in different kind of aspects. First of all, what's our use for the power device? So I think normally we talk about mission profile. What we mean is about when we operate our design, what will be the condition or what's the working profile or the stress applied to the power electronic. So for us, in terms of motion control part, the driver, the main application is for high speed, high dynamic motion system. So the stress in the transient is most on the transient power rather than the arms power. And then the stress condition is a sustained long-term operation because the machine normally operates 24 hours, 7 days, non-stop, almost non-stop until they die. So normally the customer expect the machine can be operated at least 10 years. Or even most of customers can operate the machine over 20 years. So you can ensure the machine can operate good enough, sufficient long lifetime, such that you can make sure your design can be reliable and such that you can minimize your cost of failure. And also in our assembly market, definitely the reliable is very important. Safety is important. But another way, cost and other factor, we need to always take in consideration. So, and also with the latest power device coming in, the efficiency we everyone talk about, and also we want to squeeze the machine size, all the things. They will increase the challenge and demand for the system design, and such that how we can also still maintain the reliability of the system. This is another challenge imposed to the design team as well. Okay, so also I think the speaker from Maryland also mentioned they involve a lot of testing to ensure to test, validate, and verify the lifetime. And then you can see this is all sort of this kind of test is we require the facility, time, and cost. So this also is a challenge for normal industry or normal company. So I think on the screen you can see this standard, normal standard, no matter it's a product or electronic system design development workflow. In generally or traditionally, most of the people we do the design. We have the design, And normally, after we have the design prototype, we do the verification, and in case there are any issue, we do again or improve the design continually. We take an iterative approach to improve the product such that can fulfill the reliability requirement. So during the design stage, or even production stage, or even the operation stage, we go through this kind of iteration approach to continue to improve the reliability. From our point of view, it is more on the reactive kind of approach to take care of the reliability, or maybe we can say it's a kind of failure management. But for this kind of thing, it will take a little bit long time to reach this kind of high reliability level. So instead of we do this one, we adapt our later approach is to do the proactive reliability approach. So we try to design according to the possible failure. We try to prevent the failure happen during the operation. So this is the way we want to adapt. So this on the screen you can see there's a women model proposed by a company from Denmark. So this is the approach that we start with. First of all, we understand what's actually the customer requirement. When we design, definitely I think we will start with something, the design requirement definitely bigger or larger than what's the customer requirement. But we also take into consideration is throughout the lifetime, the system will definitely have some sort of degradation. So we had the time span to see what's the rate of degradation. So we have some projected degradation periods. After a certain year, based on the custom design requirement, we expect after this kind of expectation time period, our design is still able to cover. This is the starting point we design for the requirement. And then definitely we should have certain kind of margin such that before the come out of our the system operation limit. But this kind of things definitely is a challenge. How many margin we have to reserve. Then this is always a balance between the cost and then also the lifetime. So this is a common design circle. So normally we start from the requirement, then we have the conceptualization, design stage, validation, production, and release. This is a very, very standard kind of process. So our focus is start from beginning. What will be the mission profile? What's the actual requirement of the customer, and also the operation condition. And the most important for design reliability is the center part. How to, in the design stage, how we can guarantee or ensure the reliability from this part. Okay. Maybe hopefully it's not too small. This is the design step we adapt for the company. It's aligned with our product development product life cycle test we call a stage gauge process. So this is we start from the conceptualization stage and design stage, and also the production and release stage. So, sorry. So start with the what's the understand, analysis, what's the actual requirement or the mission profile, and then definitely we go into the design stage. But at the end of the day, the important is also test can help us to verify and validate our design. So test is also very important. I'm not saying not important, but this is very also important for us to affirm our design is it meet the requirement. So let me go into a little bit more detail stage by stage. So on the right left-hand side, you see this kind of standard mechatronic system. This, in fact, this is a two linear motion stage. instrument or machine. So with the certain requirement about what's the cycling time, what kind of speed they need to achieve. This is and under what kind of operation condition. So with this one is a starting point. We need to understand the requirement. And then definitely when we design like motor driver or power supply, they have different type of architecture or circuit topology. And one more important part is that we need to assess what are the risks based on our past experience, or even some of the components we use. Recently also we try to start using the silicon carbide power device. So this is something, is a new type of the device, or some power supply circuitry topology we will also adapt from traditional one to a latest one. So this is they will pose certain kind of new risk to us. So without the previous experience, we need to have carry out some of the study before we really can face in our design stage. So second stage is before we start the design, we encourage our engineer, or even we put into as a standard process for the designer. Before they start, they need to do detailed analysis before they go into the design. So we study based on the previous experience. We understand. We pick out the failure mode, understand the failure mechanism. So we do SMDA. Also understand what kind of stress we will experience, we're going to experience, and what kind of strain we decide to counteract this kind of stress. And definitely, we also list down what's the critical component for us to further evaluation. I think Dr. Das also tried to mention about in certain kind of design, we can take out from the research paper most of the high-end power electronic power electronic system. Power device is one of the major failure account for this one. Power device normally refer to like IGBT or power MOSFET or converter. And second one is capacitor, and even the driving component. So this is some of the component we put under our focus list. Is the component we will focus. So assess the risk and also try to collect the information about the lifetime or the failure record about this kind of device. So during the analysis, we definitely, I think, before we go further, we put in the actual prototype. We try to utilize the simulation tools to help us from circuitry analysis to the electrical, thermal, mechanical analysis. I think Dr. Das and also Michael Osman also mentioned about the package. It's one of the major contributors of the failure. It's not just on the electrical stress. I think for most of the electronic designer, it's the focus on most on the electrical stress. But because we are also working in the packaging, so we also understand well about the wire bonding stress. This is one of the major failure modes, the wire bonding lift off. And also because the power device is attached to the different substrate, because they have this attachment will be involved a certain kind of epoxy and or soldering. This also can be during this kind of different type of material. They also have when they heat up the time, they experience a different thermal stress because the thermal expansion we call CTE mismatch. This kind of thing, we also can create a mechanical stress. It's not just a purely electrical stress. So this is why Dr. Dassam also mentioned the power cycle becomes crucial to the component itself. This will create a lot of important part, the failure. So this is a part of our consideration, but this sort of information is not widely available. Not every component supplier will give us this kind of information. So we try to design with this kind of fault-tolerant approach, try to take the component with sufficient quick margin, such that we can design well within the limit. But definitely, I think we also have to understand so-called physics of failure, what kind of failure mechanism will contribute to the failure of the component, also the design. We take our approach is trying to create a condition of our design or even our component selection if well within our critical mission profile, such that we can have the confidence to say that our design is reliable. So in terms of the failure, definitely I think people using a statistical-based method to try to, based on the past experience, and we also study the stress and strain, definitely this kind of distribution. So we need to reserve a sufficient margin such that we can have certain separation and also have the sufficient margin for them to take care of degradation effect. Also, we will go into the component parties of physical failure. So I think this is the approach we try to see when we select the critical component, particular power device. This is IGBT, it's a very standard IGBT module. So going into detail, they also involve the different layer of interface, the wire bonding interface and the die attach interface. So in fact, the failure mode is not just purely static temperature. In fact, it's a cycle, the temperature cycle. This is what Dr. Das also mentioned. But this is the only one of the information we can collect from Infineon. They have to talk about the power cycle capability. With this information, you can estimate what will be the stress, or you can what kind of operating temperature and also the temperature variation during the power cycling. So this can give you some idea what sort of component you can use for the application. So maybe I will go in a bit more detail. Just like a motor driver. In fact, the motor driver can be moving certain kind of speed profile, and then they will involve certain current waveform. The current waveform, in fact, the current provide the electrical stress. But when you take the power of this electrical stress, they will in terms of the thermal stress, and then we in terms of the mechanical stress of the packaging. So this is create a so-called delta temperature here. So this is pose the stress to the component. In fact, it's not on the die itself, but on the interface. So this is some idea we need to take into consideration. So with this one, we can select a higher margin component, or are we able to smoothen the profile, the stress? This is always a trade-off between the component selection and operation condition. So this also is become the design consideration for the team. Definitely, after you have the design, we need to determine we go for the design verification. So previous speaker also tried to mention about the accelerated test, include the accelerated life test, environmental stress test. So important is how to determine the margin, the range, up to which range we're going to test. So how to define the test range is become another art. So this is something based on our operation condition, our previous experience, and also some of the testing standard we are using. So this is what we are doing in the company. After the design, definitely we have the prototype. We will go through the standard functional test and system integration to ensure the performance reach to us. But the final one is definitely we need to go for so-called reliability test. Is how to verify the design is it. So in general, we go for the temp cycle and power cycle and SRI test to try to predict the reliability. Vibration is another one because normally the electronic system, we want to make sure the fitting and mounting and also the soldering will be reliable enough for our design. It's not just a electrical part, it also is the mechanical stress as well. So after the prototype design verification, we go for the, before we release, we also walk through another round of the design analysis to ensure our final design is meet our requirement. So the design validation is try to utilize the particular hash test. This is called highly accelerated limited test or live test. We try to squeeze the design, the limit. We go beyond our operation limit, try to look for the weakness part of the design. So we go beyond the operation limit, approach the destructive limit. So we can give us an idea which part is the most wicked part of the design. Through this one, we can evaluate our design safety and reliability, and also how robust of our design. And then this kind of the design approach can help us to go into the next stage during the mass. This is a mass production. How they determine the hash test to how to during the production, how we can screen out the manufacturing fault. So this one is what we are currently doing, how to do the hash test with the Hong Kong PC. So they offer us the facility to carry out the test. So these are the tests we adapt into our production. So I think we walk through the functional test for our power supply and the power motor drive. And we also had we not yet go to the hash test completely, but we had the part of this, but we had the burn chamber can operate the temperature and the stress up to close to our operation limit to try to squeeze the manufacturing or assembly fault. So lastly is when they're going to release with the latest the power drive design, we adapt a more intelligent one. So we managed to can add in some of the so-called sensor inside to monitor the real-time monitor the health condition of the design. However, this is costly. We need to selectively to do it. Our design may not like a wind turbine or maybe not safe that kind of EV kind of the safety condition. So all the measurement or this kind of health condition monitoring is the involved cost, and also the resources we put in. So this is something we need to trade off between is this necessary or not. So if we can design highly reliable one, this will become arguable. We need to do the real-time health condition monitoring if your design is reliable enough. But anyway, as a company, our direction is to provide a smart factory solution. We not just provide one equipment, we provide a whole assembly line. Every machine or individual machine or individual subsystem, in case a problem will affect the whole line operation. So this kind of holistic health management or machine health condition monitoring become getting more and more crucial and important to our customer. So this has become another direction we need to go for in the really long run. So I think this is something we can have a lot of room to cooperate with CARES and CARES in this direction. So I think as a summary, as a normal industry, we're interested how to have a reliable design. And then they will involve for power electronic, some very critical component. The critical information is not widely available. How we can know that what's the critical lifetime and the life prediction. So I think this is if CARES can offer this size solution or provide the information, there will be benefits to the Hong Kong or local industry. I think this is something we would like to explore the opportunity to work with the CARES or CARES on this direction. Okay, this is to the end of my presentation. Thank you.
Thank you, Mr. Peter Ng, for your remarkable presentation. For all the participants, you are reminded that you could scan the QR code that would appear at the bottom right of your screen, and that you have any questions that you feel free to ask both speakers within our room here at the Science Park Care Office, including Dr. Stan McCoff and also Mr. Peter Ng. Okay, let us see if there's any questions coming through now with my pack in front of me. I think in the presentations, there's a lot of things that both speakers share with the audience or with the participants. So I got, at the moment, quite some questions for Dr. McCoff. Maybe I put up the first questions. So the first question is asking, how is the performance of the thermal camera being used in outdoor applications, such as surveillance and building wall and pipe inspection by drone? So see if you have anything.
There are several layers in this question.
Yeah.
So first of all, how is the camera used? I take it as a more generic question. So thermal camera obviously doesn't need daylight in order to operate. There are different thermal signatures in different places of the world at sunrise and at dawn and at middle of the day. But basically contrast in the thermal image is created by the surface temperature. And so this leads me to the second part of the question, how it is used for wall inspection and what else? Building and pipe inspection. So basically, there are two thermal phenomena that thermal camera can recognize. One is the amount of heat that is accumulated and the corresponding temperature of the body emanated through the surface. And so if you have, let's say, a pipe with a small leakage, you may not see it, particularly if the pipe has transparent liquid being lost through a small crack. But typically, both the temperature and the emissivity of the materials that are involved will help to create some contrast so that one would see difference at the point of the crack or damage, whatever. For walls, there is an additional thing. Basically, another phenomenon that is related is thermal conduction. And I'll give you a specific example that a very recent inquiry into our product made me realize. So you may be familiar that there are a lot of cases in Hong Kong of tiles falling off the towers, and that has been a big problem recently. And so it turns out that there is a way to monitor that passively with thermal camera and figure out which are the tiles that are about to fall.
Spouting, yeah.
Yeah, so what happens is there is a bonding glue, let's say, or some sort of yeah, at the back of the tile. And what happens is when the tile is not well bonded, it's about to fall, the thermal conduction with the wall is different.
Yeah.
So if you're observing the diurnal temperature cycle of the wall, you would see a spot where things lag behind, because this particular tile is not connected to the wall, which has large thermal capacity, and so will respond more readily to the immediate ambient temperature changes. And so that is another way of using that for wall inspection. I hope I answered that question.
Yes, this is also very interesting for this, thermal imaging technology in the applications for smart cities regarding the buildings, because in Hong Kong there's a lot of high-rise building everywhere. Okay, so then I got a second question, which is, how critical is the sensitivity degradation to the module or solutions in terms of usage? That's for Dr. Markov.
So it really depends on the application. And I think I can come up at least with 3 examples right now. Suppose that you're interested to know the traffic of people. So you're monitoring really how people move, the density, the speed with which they move along a certain corridor or in the office. For that, you're not so interested in the absolute value of the temperature that you're detecting. So what you're interested in, some contrast really that helps you distinguish that there is a person in this environment. So a person will generally appear as a hot object. And let's say typical office, you have the ambience at around 21 degrees and skin temperature, a healthy person will be around 33, probably clothing will dump down to 28, 26 even, but still distinguishable. So if your sensitivity degrades over time, instead of 26, you may read 25. That's not a big deal. Yeah. In this application, sensitivity degradation, at least to a certain degree, is quite acceptable. Not breaking the functionality. But on the other extreme, you have a thermal camera that is mounted somewhere and screens the flow of people and has the particular objective to detect people with fever level of temperature. So you really want to pinpoint people at around 35 degrees skin temperature. And if you drop 1 degree, all these people will pass by as healthy. Of course, you can detect that because you would observe that your major flow of people, assuming majority of people are healthy, why would they come to work otherwise? So they would have, instead of the normal 33 degrees, their temperature would drop to maybe 31. You have to question that, I mean, in your application. But that is the reason we are looking into that type of problem with CARES, to find out models that can be small enough so that they can be put even in an embedded system, or let's say an embedded system 5 years from now will have dramatically higher resources. Or occasional data extraction from the sensor to a centralized server where a more sophisticated model can be learned to detect these type of anomalies, that overall the temperature of people drops down, and try to correct either within the application or just as I mentioned, our sensors contain calibration data, and so this calibration data may need to be retuned to correct, compensate for this. But the reason we need to bother with this is because we now can produce sensors in quantity that allow and at cost that allows deployment of thermal imager modules in infrastructure environment. So the whole building, multiple rooms and so on, where this becomes important. If it is just for a mobile phone attachment, it doesn't make sense to invest that cost in training model, deploying it and so on. And there is no data enough from one single device. So that makes very interesting this collaboration potential.
There's enough questions for you. Actually, it seems to be you answering another question, which is asking about calibration. You addressed this part as part of your answer to the last question. So maybe we save some time to have some questions for Peter from the audience. And the first questions that is asking Mr. Peter is about how do you consider the third generation semiconductor material such as silicon carbide on the reliability development of power modules or related manufacturing equipment? So this may be a challenging question for you.
I think this one is another challenging, really a challenging question. I think silicon carbide definitely, or maybe not just silicon carbide, we talk about, besides silicon carbide, also gallium nitride. This is something I saw on the slide. The packaging normally is a high power device. So the temperature wise, and then there were high density temperature. So the assembly of this kind of power device become challenging. So within the company, we have the silver sintering for the substrate kind of bonding. We have the high power heavy wire bonder, aluminum wire bonder. We also investigate for different type of wiring material, such that ensure the bonding and the bonding with the die metallization ensure a good consistent bonding. And certain applications we're using the clip bonding or using direct link bonding. This if we can have the bigger area, so such that they can have the people will perceive it more reliable and also provide the thermal, reduce the thermal stress. So, and also we have the molding equipment for the molding, such that can reduce the moisture effect and also make sure the heat can properly evenly dissipate out. So this is something is from packaging of machine process point of view, we can work together with the packaging designer or the component manufacturer to improve the reliability.
Okay, I think this is a very good answer indeed. Okay, so this is another one for you, Peter. I think this is a less challenging one. It may be easy for you to deal with, but we have to deal with it seriously for reliability issues. So very pleased to see your presentations regarding ASM's various approach in the whole product development cycle regarding reliability. And an audience is asking how long, in general, does it take to design and verify the reliability of the power modules? Is it an easy question for you?
This is another challenging question.
Okay, also challenging.
I think for currently, verification is one part. Validation is another part.
Yes.
Normally, verification, we do all the functional tests is relative, is manageable.
Yeah.
But experiment life test is just like what Michael Osman mentioned, to determine the time and also the stress level.
Yes.
It's also challenging. Yeah. Normally, we based on some of the data standard, and we based on our past experience, and also the field operation condition to determine what will the stress level we impose for the experiment lifetime test. And in terms of HASS test for the validation, frankly speaking, we're still a learning stage. We learn together with the Hong Kong PC, and maybe later we can work together.
We can support you,
yeah, to understand how to define this HASS condition, up to what kind of range. Such that we can, using this one to do the prediction of the line. I think this is a lot of area we can work together with the KS on this one.
Yes, sure. So, and your answer is very good for us to collaborate in the future. Okay. So before I hand over to Professor Yong for a closing remark, perhaps I got a question which seems to be Professor Yong, you addressed that might be more appropriate than maybe Mr. Peter or maybe both can have their view in response to this question. So this question is asking, what KS would collaborate with the electric or electronic industry? That's the electronic industry is at the part, but I think electronic and electric industry is closely related together to enhance the product reliability? So I think this is a very good question, maybe also for all of the speakers, including our center directors here. So maybe who could respond first?
Well, maybe as the host of the webinar, I'd like to say a few words on this question, and then our partners, actually, Stan and Peter, their companies are now our collaborating partners as well. Now, the mission of CARES is to enhance or elevate the reliability and safety of products, components, and even systems who are made and commissioned in Hong Kong. Now, the two companies, we have speakers on that. They have products, they have design in Hong Kong. We try to help and collaborate in order to make their products even more safe and more reliable. We're using AI techniques, reliability modeling, data-driven methodology, POF, to enable that, right? So in our last few months' work, we also told the industry that our work is equally applicable to every industry. Now, of course, electronics being, I think, the most valuable industry in Hong Kong, take up the most GDP in Hong Kong, would be one of our main focus. And actually, out of our 20 parts industrial partners right now, who all signed the NDA with us, I think 3/4 of them are from advanced manufacturing and electronics industry. So that tells CARES is ready to help the local electronics industry. So I let the two partners to say a few words on how CARES can help you. Stan and Peter.
Okay, thank you. So first, I believe I mentioned our idea or working concept that we are exploring with CARES. CARES can help in two ways. First, you guys are aggregating equipment that is helpful to get access to, and second, you're aggregating expertise not just within the realm of the data modeling, but through your university collaborations, you have access to expertise where different groups tackle different physical phenomena related to reliability. And this is very important because, we can predict lifetime, possibly just by means of data modeling. But suppose we are short of a few years or a few months. What do we do? Yep. Unless we gain access to physical understanding, we don't know how to make informed decisions to change either the design or the process of manufacturing in order to deliver the lifetime expectations of the final product. Yep. The other trivial thing is that we don't sell to end customer, but our customers who produce the final product embedding our thermal camera modules may also need to accelerate their product development and incorporating these predictive failure analysis in their software. So we on our own will not be able to deliver such models in a cost-effective way. But throughout this collaboration, we can transfer a lot of this effort and deliver to customers without augmenting the cost of our end product unreasonably. So that's quite important, actually.
Thank you for the commendation.
Was already mentioned by Dr. Osman and by Peter. The optimal effort and
I think today is we're talking about power device mainly. So I think in my presentation, also I think it's Osman presentation, they also talk about or even Dr. Das presentation. The power device, one of the critical assess the lifetime is the power cycling. when doing the power cycling, it's not simple equipment can do it. I think cares at the equipment can help to investigate critical power device, the lifetime, during the power cycle, what will the stress create. And through this one, we can have the chance to really measure the lifetime as well. So this is part of one of the part where we can collaborate with. Yeah. Because this one, the information is not easy to obtain from the manufacturer. Yeah. The normally manufacturer not willing, I'm not so sure they're willing to disclose this kind of information to us. Yeah. Yeah. So with this information, we can have the understanding of the risk of failure, such that we can design within the limitation. So I think for select component, this can be another one. But then I think some audience answered the question about from packaging point of view. Yep. We also work together with this power device manufacturer to improve the process. Yeah. So with this kind of equipment together, or this testing facilities in KS also can help us to understand the process, how to ensure what's the process window can help our customer to provide reliable assembly process, yep. So they can have more reliable components.
Yep. Yep. Thank you, Peter.
Okay. So, I first, well, not first, but we thank both, guest speakers, Dr. McCoff and Peter for their sharing. And then I think we come close to the closing remark part, and I'll pass to Professor Yong, our Center Director for CARES, to offer a closing remark before we end this webinar.
Okay, thank you, Richard. Well, first of all, I'd like to give our hearty thanks to Stan and Peter, who spent the whole morning in our CARES office, attending this seminar and giving talks to the audience. I also want to give hearty thanks to Dr. Das and Dr. Osterman, who may be now sleeping back in US. If you add the 4 webinars together, that really supplement to each other. And in fact, our 2 industrial speakers on my left-hand side, they have some common interests. For example, Stan mentioned on and off about bonding or wire bonding problems. And next to me, Peter is a wire bonding expert. So after the webinars, you two can share, right? So I'd like to give a few minutes remarks to the audience. Last but not least, I'd like to thank also the audience online that stayed with us in the whole morning. Now, apart of giving thanks, I'd like to also mention about the uniqueness of these webinars. Today, we're talking about power electronics. As Peter just mentioned, power electronics actually is applicable in all industries. The larger one would be power farms and windmills and EV, electrical vehicles. But if you look at every electronic systems, or even a robotic cleaner, we have power electronics, right? And well, with power electronics, we have a lot of good products. Actually, we talked to the government whether Hong Kong should have a center for power electronics. I think Peter knows what I'm talking about. Well, but as far as component level or module level is concerned, Stan gave us a very good introduction on their new products. And actually with their modules, it sounds it will help not only on reliability of products, but also it affects human life, right? You're talking about examples like COVID-19, right? So hopefully, Stan, with your company's new products, we'll have all facilities reopened because of your checking COVID-19. Of course, we need vaccination, right? Well, best working together. Yes. Well, with vaccination and with your product, infrared sensor control, then hopefully Hong Kong will be a better world in the months to come. Now, last 2 minutes. The vision of CARE, as I just mentioned to my partners, is to help the local industry to elevating and promoting safety and reliability of their products and components and systems. We are funded by the government. We have a mission that whatever we research, it should be applied in nature. That means it should be equally applicable to different industries. I'm glad to tell that at the moment, we have over 20 industrial partners from different industries. You name it, like advanced manufacturing, you name it, like electronic industries, you name it, like a smart infrastructure. We just signed an NDA with a company who is doing inspection with infrared sensors on smart infrastructure and smart buildings. So that may be something we can collaborate even more. Also, we have smart transportation, smart utilities. You can, the audience online, you can browse our website, you will see more. Now, not only from our industrial partners, actually we are forming a consortium. Actually, different partners from the industry, they can work even or collaborate on their own, right? Helping each other. But more importantly, we have just signed a collaborative agreement with our counterpart in US. The two speakers, in the morning has just mentioned that from University of Maryland. So with their backup in fundamental research, our research will be even more rounded with different expertise. Apart from manpower, that we have many researchers located in Science Park, we also have 2 laboratories housing over 20 to 30 very critical equipments on reliability and safety. Well, at the end of the day, we want to tell the government that with our collaborations, whatever we design in Hong Kong, whatever we manufacture in Hong Kong, whatever we commission in Hong Kong is #1 in safety and reliability. So with that final remark, I'd like to thank again all the audience online and thank again our local industrial experts. Thank you.
Okay, thank you, Professor Yong, for his remark, and also that brings us to almost to the end of this webinar. So it will be our pleasure to have the heartfelt appreciation to all our speakers, technical support, collaborating organizations, and supporting organizations for supporting the webinar. And I hope all of you found this webinar beneficial and valuable throughout the webinar in the topic of reliability enhancement of electronic parts, products, and systems. So in fact, our CARES will have upcoming webinars that will be held sometime in April. So I hope all of you will watch out for our future announcements for our upcoming webinars or other activities. So I wish you all a pleasant day. Thank you very much, and see you again.
Bye-bye.
Bye-bye. Thank you. Okay. That's it? Okay, that's it. Thank you.
Thank you. So good.